In this video, we will take a look on how to set up CAD simulations for gravitational water vortex power plants. So here, in this gravitational vortex power plant, it has an inlet channels where the water is coming in. So over here, we have the conical basins attached to that inlet. So the water coming into these basins, inside the basins we have a turbine, and that turbine will extract power from the waters and it will rotate. So the water coming into these basins, it will rotate, it will push these turbines, cause the turbine to rotate, and after that it will exit through the bottom of these basins. So the idea is to use a CFD simulations. In this case, we'll use FLUENT to simulate the fluid flow within these power plants, and also to simulate the rotations of the turbines in order to estimate the power output of this particular design. So this is your ANSYS workbench. We can create a new workflow for your FLUENT. Now these are the 6 steps that you have to take in order to complete your simulations, and each of these steps will require a separate software to do it. So the first step here is creating the geometries. However, we have the geometries. What we need is to import the geometries from our SolidWorks into your design modelers. So this is your design modeler. Go to import external geometries, import your geometries from your SolidWorks, and generate bodies. So here we got 4 parts, 4 bodies inside. So we got this solid body of your entire geometries. We got cylinder 1, we got second cylinder, we also got the water turbines. So what we actually need is only just 2 bodies, one for the domain itself and another actually for the rotating domains. So the cylinder inside these water turbines will be responsible for the rotation of the turbines. Okay, so we created this cylinder specifically to take care of the rotation of the turbines. As you can see here, the turbine is actually inside the cylinders. So what we can do is we can make use of this cylinder okay, to create your first domains. So we can take these 2 cylinders and use the Boolean functions and do a subtractions. So the target body will be this. Your second body will be the cylinder itself. Okay? And you click generate. So you can rename this one as a domain. This will be your main domain, and we can hide these 2 bodies first. If we create a section plan, and we're able to see now your domain inside now will be hollow. So this hollow part will be your rotating domain. Okay, your rotating domain. Now we need to create our rotating domains. We need to do subtraction as well. So your rotating domain will subtract from your turbine. Okay, so you can rename this one as your inner domain, and show the body, and we can create some Boolean expressions. So the target body will be the inner domain. So you can hide this one first. The target body will be the solid, applied. The inner body will be this, applied, and we click generate. Now we have the inner domain. If we do this section plan, we will see now also the turbine part will be hollow as well. Okay. So once we done that one, we can save and exceed. Now the second step will be meshings. So we can double click this one, meshings. So in these steps, we will do two things. We will create the boundary conditions and also prescribe meshings into your domain. So what we can do first is to create the boundary conditions. So we can select all the surfaces. We know that the surfaces will be the wall. So this will be the wall, all these things. All these surfaces will be the wall. You can right click and create a name selections and call it wall. So it should appear here, the wall. The top part will be a symmetry. So you can create a name selection as well and call it the top surface. This will be your inlet. Call it inlet. This will be your outlet. Call it outlet. Okay. Now the remaining thing is your turbine itself. So what you can do is you have to name your turbine as well. What you can do is you can click on this body and try to hide it. Okay, and click on the surface. Hide the surface as well. This will be the surface, the interface between your rotating domain and your main domain. And we can just hide this one, hide it. And what remain will be your turbine, which means we need to select one by one. So we need to select press Ctrl and select all the surfaces. Make sure you select all the surfaces, you don't miss any. Now we selected all the surfaces, we create and name it as turbine or runner. Okay. We can show all the bodies now. So we got 5 boundary conditions, one for the turbine, one for wall, the top surface, inlet and outlet. So what we need to do next would be creating the meshings. So there's some detail here. You can include what will be the expected mesh size. So we could start with 0.015. And try to reduce the skewness as well. Okay, and we can generate and to see how it looks like. So this is a tetrahedron mesh. Okay, and you can go to the statistics and to also see how many elements that you have. So if you're running a student versions, make sure that this does not exceed 512. This does not exceed 512,000 elements. Otherwise, you're not able to run your cases in FLUENT. So this particular mesh distribution looks quite reasonable. What you can do next is you can do the section plan. So create new section plan, and you're able to visualize in fact what your mesh looks like inside your domains. Okay. Now it's also possible to visualize your section plan in the Z directions. Now you can see how your plan looks like through the cross-sectional area of your basins. You can edit also, move it up and down to see how it varies, how your mesh varies. In the Y directions, now what is important now is the boundary layers. All your walls will include boundary layers. It is essential that you include boundary layers in order to solve the flaws. The flaws close to the wall accurately. You need boundary layers also for your turbine. It will be particularly important for your turbines, your boundary layers. To create boundary layers, you will need inflations. So you can click on your domain, okay, and click on the boundaries. Now select all the boundaries. So press on the control buttons in your keyboard and press and click on all the relevant wall These are all the wall required boundary layers. Okay, and click apply. So you're gonna do 4 layers of boundary layers. So we're gonna need a boundary layers as well for your turbine. So what you can do is we can hide this body, hide your first body. Now you're able to see it. Hide this particular surface as well. So okay. So what you can do now is actually now you can click on this one for your body and apply it, and then proceed to select all the surfaces that you require the boundaries. So you have to select. You can hide your mesh so that you can select all your surfaces more easily. So you need to select, in fact, all the surfaces that of the turbine would require boundary layers. Okay, so that will be everything, and click apply, and you can have 4 as well. Now you define all the boundaries. Click show boundary layers for all the wall. You can proceed with mesh generations. So you can observe the boundary layers now is created at all the wall. Okay. You can do section plan 1, and you can see the boundary layers is created at the wall of the conical basins, and also at the inlet. So the top surface is going to be symmetry. You do not need the boundary layers. You do not need the boundary layers for the interface as well. Interface between your domain and your rotating domain, you do not need it. So you can see here also the boundary layers for your turbines in your section plan number 2. So you can see the boundary layers is created. It's created with your turbine. Okay. So you could try to improve the quality of the meshings a little bit. So you have close to 200,000 of elements inside your domain. So you can also go to a mesh and go to metric graph here and check actually the elements, the quality of the elements. So you can go for the skewness, and most of your mesh in fact are less than 0.5, so they are considered quite good, and you can click on this bar to see where are the poor quality mesh actually are located. It is mostly at the edge of the turbine. Okay. However, there are the elements of the mesh with high skewness. There are not many. So if you are happy with your meshings, you can save and proceed to FLUENT. Now we're done with the meshing, we can proceed to FLUENT. So let's try it again. Maybe we try to update the mesh. Now it's done. So your domain now is ready for simulations. So now we have to set up your model. Okay, so check that you have actually two domains, one inner and outer. So you're gonna have gravity in the x directions, in the y directions. So specify your gravity, which is important. You're gonna do a transient, static simulations. So the fluids will be waters. You will need waters. Go to FLUENT database and go for water liquid. Okay. So this represents the interface of your rotating your domain and also rotating domains. You should have two. So you have to specify your inlet velocity. We'll use 0.15 with intensity of 1. Now we have all the setups. Your top surface will be symmetry. We will use symmetry for the top surface, and we have to change that one as well. So go to your boundary conditions for the top surface. You can change it to symmetry. Okay, and apply. Now, the important part is your dynamic meshings. So click enable dynamic meshings. So we will do smoothing, layering, and meshing as well. So we will increase the layering. We will do remeshings here. And copy your minimum maximum length scale into here. And go for maximum cell skewness is 0.5 or even lower. Now we enable the 60OF. Here we can create a profile for 60OF. We can create one and call it the turbine. It's gonna be just one UOF rotations. And you specify your axis. Axis is 1. Is along the y-axis. Okay. The rotations, center point of rotations will be 0, 0, 0. And you will need to specify the moment initials. The moment initials, you can get that information in fact from SolidWorks. And you can get informations for the mass from your SolidWorks as well. So you open up the SolidWorks for your turbine. Okay. Go to edit material and make sure that you choose the right material for your turbines. So in this case, it will be a steel. Then go to mass properties. Okay, and SolidWorks able to provide you the mass is 2.73 kg, and provide you the moment inertia as well. The moment inertia should be 0.01. So 2.73, and this will be 0.01. Okay, so you have a turbine. Now you need to create your dynamic mesh zone. Your domain will be a deforming domain. Your inner domain will be a rigid body. So it's a passive. Click create. Select the turbine and click create. Now select your turbine. And ensure that this is ensure you deselect the passive. Okay, so you have all these 3 dynamic massing zone now, you are actually almost ready to simulate your case. So you can use a second order for your turbulent equations. So this is your turbulent equations. You will need to initialize your domain with an initial values for the variables of the equation that you're solving. So you can prescribe some value, some small value for turbulence. Now what we need is to actually set up few things. Set up the results so that we can observe the results when the simulation is running. How do we do that? There's a few things that we need. We might need to look at the velocity profile. We might look at the velocity profile within the domain. We might need to look at the meshings, how the meshings actually changes during the dynamics, during the rotation of the turbines. We might need to also look at how the moment change. What happened to the moment of the turbines? When the turbines rotates throughout the simulation. So those few things that we can do. We can go to we can create a plan. So we can create a plan that can actually cut through cut through the cross sections of your domain. We can do this one as well. So we got two new planes now, and we can plot a new contour. Maybe you can call it a pressure, a velocity to the plane number X, and display it. Okay, so there's no velocity initially. There's no velocity. So we can actually try to manage this. We can try to create a new one, maybe. can go to your contour. So reselect element 10. Okay, now we can actually see the entire cross-section areas. Okay, this is the velocity contour inside the domain. We can click save. Okay, so we might need a meshing as well. We can do a meshing. So we can see the meshings maybe from the plane number 9. Okay, so okay, and adjust a little bit so that we can see the mesh inside. And use the color that you're actually able to see. Okay, now we're able to see. Actually save it. Okay, and we can create actually multiple window. Can create we can create 4 windows. So we can create such projections. We can use one window to see the meshings and one window for the contour. This one. Now we also may be interested to see the moment. So we can go to a report plot and click a new one. This will be your turbine moment. Okay. A new definitions, which is a force, a moment force that is along the y-axis with a moment at center of 0, 0, 0 for your turbine. So we can name this one as turbine moment as well. And I will create a report plot and report files. Click OK. So yeah, we actually don't know this anymore. This is it is ANSYS has created this one for us. Okay, this will so basically your turbine moment will be calculated in each time steps. Okay, and that moment will be outputted to these files called turbine moment R files in your computers. So this is the report files. The report plots, these functions will it will output the value of your turbines onto one of the window here. Okay, it will output one of the turbine, the value of the turbine moment into one of the window. We can select that window. We can set that it is it's one of the window. It could be window 3 or window 4. Windows 6. There's actually no data for that. Well, at the moment there's no any data. When we run it, then we will have the data. So there's no data available to display. Okay, so we can run this. Where we can save also how many files that you need to save. Okay, so you can save for each time step or save for every 5 time step or every 10 time steps. So saving the files, is important, especially you wish to create an animations. Okay, if you wish to create animations, you will need the data to be saved for a particular interval of time steps. So this is where you run it. You need to specify how many time steps you need to run and what will be the size of the time steps and how many iterations that you need. It is always recommended not to run too large time steps, otherwise you're not able to observe the rotations of the turbine. So if you use 0.05, okay, this will run up to 25 seconds. So as a start, it's always good to use a smaller time step, like 0.01. Otherwise, you would have a difficulty in getting convergence. So this is a plot of the moment turbine moment. So we can see here, this is the residual of the equation that you're solving, the continuity, the momentum equations, as well as the turbulent equations, K and omegas. So here is a graphical representative of the residual, and we can see that the solution is converging well in each time steps. So we use a small time step here of 0.01. Now there is a huge fluctuation here in a moment is due to is due to the solutions, initial solutions. So as you progress and your solution become more stable, you will see a less fluctuation for your turbine, for your moment. So to run this one, you need to run for many time steps in order to capture the rotations of the turbines. Now what we can do is we can visualize also your mesh. So here we can see the mesh. So we can go to execute command, and use display object display followed by a space and the name of your mesh. So click OK. Let's try with somewhat larger time steps. So we can observe actually the rotations. So we can try maybe with even larger time step to see a more pronounced effect with perhaps 0.04. So another thing we can do is looking at the velocity contour that we just created. So we have this velocity contour. So this has a name of contour 1. What we can do is we can go to execute command and use contour 1. Okay, and calculate. Now we can see how the velocity is changing inside your domain in each time steps. We can track also the turbine, how the turbine is rotating. So we can see sometimes we can see the gap, and that actually represents the turbine itself. Now we can see how actually we can restrict actually the range. Because of the initial effect, you can see because of the initial effects, there is a huge spike in the initial moments, which is not true. So we can try with minus 0.05 to 0.025 for your y-axis. So plot, you will see a smaller range, and you'll be able to see actually the fluctuations of at the moment. This is still maybe a little bit too large for the moment. So if you continue to simulate we should be able to obtain a moment with such a characteristics. So at some point you will get the same moment that it fluctuates between the negative and positive moments, right? So it is possible to save the data as well to create some animations. If you save the data, if you run it for a very long time, eventually you can also post-process your results in these results sessions using post-CFD post-solutions solver. Okay. So that will be all for this videos, and I wish you all the best in your setting up this in running the CAD simulation for this gravitational water vortex power plants. Thank you. See you and bye bye.